is Thibaut from France. So he's talking about sampling from Wasserstein Barycenter.
Thank you, and thank you for the invitation and for this whole workshop. I've learned a lot. It's very interesting. So thank you to the organizers. And I hope I'm going to interest some people in this problem here. So it's a problem I've been working on for like maybe a year, but we are kind of stuck. So I've been working with Chieb Daloul, Magali Tournu, and Jacques Liandra that are in Centrale Marseille. So sharing what we've done so far, I hope that it will catch your interest and we can go we can move and find something find more results on this problem. So the problem that I'm interested in is sampling from the Wasserstein Barycenter. So I'm going to start by defining the Barycenter. So the Barycenter is a notion of average. So I'm just going to look at the definition of averaging. Oops. Yeah. On RD and try to see how to extend it. So when I have a bunch of points on RD that are my xi, I want to find a point in the middle like that sum up all my my data. And for that, we use the average that happens to be also the argmean of the variance, what do we call the variance of my data, which is the argmean in X. And seeing this definition, I'm allowed to have a definition of my averaging depending only on my distance. So this is a Euclidean norm. And allowing this point of view, or from this point of view, I'm allowed to define the same thing on the sphere. So on the sphere, I have a geodesic space. The sphere is a geodesic space when I look at the angular metric on it. And when I have points on it, my xi is here. If I denote by, so S is my sphere and D is its metric, then I'm allowed to define what do we call X bar, my average, as the minimum of the distance between xi and x squared. Again, this is what is called the Fréchet mean, or the Barycenter of my points, that allows me to define averaging into geodesic spaces or metric spaces. Okay, so the space that I'm interested in is the Wasserstein space. I'm just going to quickly remind the Wasserstein distance, even if everybody knows what it is here, just to set up the notation. So I have two measures, mu0 and mu1 in my Wasserstein space, my space of measures with second order moment. And I'm looking at the infimum over all couplings that I will denote gamma of mu0, 1, all the couplings between mu0 and mu1. And I will denote by a little gamma all such couplings. And it has three properties that I will use. This Wasserstein space is a geodesic space, just like the spheres that I mentioned before. It is positively curved, just like the spheres I mentioned before, and I will use this sphere as like a stereotype of my Wasserstein space to make some drawings. And when mu0 is absolutely continuous with respect to the bag, then my gamma star, that is the optimum here, has this Brownian map. Okay, that I denote T from mu0 to mu1. Okay, now from that I have my geodesic space or my metric space on which I can define my Barycenter. So I have my measures mu1 to mu0, that are probability measures. I can associate weights that I have a slightly more general definition of Barycenter. And I can look at mu star, I define mu star as an argmean of my average distance that I will write here f of mu is a function of mu, and I will look at for the mu, the measure mu that was centered in my data. So I minimize this variance of mu. Two things here, the Barycenter always exists. So this was proved in the paper of again Carrier, who introduced the Barycenter in the Wasserstein space. But it's, however, not always unique, and that will be one of the issues we have, that we will have and try to deal with. And so the question we're interested in here is how to compute this mu star from the mu I that I have. So there are different settings in which we can look at this problem. The one that is probably the most commonly studied is the one was mu i's, the measures from which I want to take my barycenters, are Dirac masses, or like a sum of Dirac masses, or finitely supported measures. And from that, I have my n measures supported on big N points. And then my coupling will be a tensor. And we've seen some talks about it earlier. I can use a different kind of algorithm, including a synchron algorithm, to reduce this tensor to something with a less dimension. But this has been proven to be NP-hard. To compute the barycenter or to approximate this variance has been proven to be NP-hard when you look at the number of points, the numbers of marginals, and the dimension by Jason and Henrik that were here earlier this semester. And so we're going to try to take another setting where instead we suppose that the xi's that are above are actually drawn from a sampling procedure. Like if we suppose that are drawn from a sampling procedure, we have more knowledge, like we have this actual sampling procedure, or we can create our own sampling procedure. So suppose that we have instead access to, let's say, the grad log of mu I for each of the mu i's. Now, how can we sample directly from mu star having this knowledge? So one typical thing would be by first sample my mu i's, and then I do what is already done, but we know that this is NP-hard. So can we do better in this setting? To come up with an algorithm for this, we will look at the multi-marginal formulation of this problem, which was also introduced by Aga and Carlier in the original paper, which is pretty simple to prove and to define. Yes.
So what is so you said something is NP-hard, so it's about it's not about sampling, right? It's about computing the base.
So there are several things that are, so I'm not an expert in this. I don't know if somebody can know better about this, but like here, the NP-hardness is to compute the actual value of the variance itself is already NP-hard in the dimension, the number of points.
And the input, like the distributions that you want to average, they are given by Diracs like that, or they are given by, I mean, they are supported by, they are not continuous. I mean,
no, yes, yeah, they are finitely supported.
Finitely supported, and okay, all right, okay, thanks.
So it's this value that is actually NP-hard to compute, and also the mu star. So yeah, this multi-marginal formulation gives another point of view on this problem. And it's saying that, so this is, if I recall, this is like the variance of my problem, the one that I'm trying to minimize over all the mu, can be rewritten as the average of, or the integral of some cost function C, that is just defined right here, which is the variance of my underlying points, integrated with respect to gamma. And gamma here is a coupling with n marginal that are fixed, which are my n measures from which I'm looking for the barycenter. And then once I have my gamma star that is solving this problem here, I can push forward this gamma star, or I can push forward this gamma star with the average map that from x1, xn gives me the sum of the lambda xi. And this gives me the actual barycenter mu star from my original problem. And so the naive thing that we wanted to do here is, well, we have another formulation, which is simpler, and we want to look at a gradient flow, gradient descent, a Wasserstein gradient descent of this second problem, the multi-marginal one. However, here we have a constraint on the marginals. So to make our life simpler, we just added a penalization on the marginals. And we arrive to this formulation of the problem, which is not exactly our original one. So we have an extra alpha that will account for the penalization. So we remove the constraint on the marginals, and instead we say we're going to minimize this same problem without constraint, but instead we have this penalization that is that we chose to take in the chi-square divergence between gamma I that are my marginals of gamma and mu I that are the marginals that I want to have for my margin for my Barycenter. Okay, so let's just start to compute this. So I'm not gonna remind how to compute the Wasserstein gradient in general. I'm just gonna give it here. So my F alpha is what I recall here. And I want to take the gradient. The gradient is, I have a first term that is just the gradient of this part. So now I'm looking at the gradient with respect to gamma, my big measures that belongs to this space. Sorry, written here. So this is a function that goes from RDN to RDN, this first function. And then here I have the gradient of each of my chi-square. And this is a gradient of gamma I over I, except that here my gamma I are from RD to RD and not from RDN to RDN. So what I mean when I write this is actually I have a big vector field that is valued in RDN, where I put 0 everywhere I is different from, or J is different from I. And here I put this gradient. Okay, so at the end, what I end up with is my big gradient is alpha lambda I lambda 1 gradient of gamma 1 over mu1 lambda n gradient of gamma n over mu n. Okay, so this is what I would like to implement for doing a gradient descent of my function f alpha. So I cannot do that because I don't have access to gamma I, which is a function where I'm at. And to do that, I do I canalize this thing. I do so we will end up with what is SVGD that has been introduced by Liu and Wang in 2016. And what I do is I replace here this gradient by the same thing convolved with a kernel. And with an integration by part, I can see that this is equal to these two terms. Why do I do this integration by parts? It's because when I do this, I have here an integration with respect to gamma I, which are my marginals of my current measure gamma, which can be approximated by the average with my particles. So this is what I do when I write here. I don't know if it's not too small, it's a bit small, but it's going to be bigger on the next slide. So these two things are like approximation of this integration with respect to gamma I. And so I have, at least for now, a continuous time algorithm that I can implement approximately. And so this is just the Wasserstein flow that I would like to implement prior to the canalization. And once I canalize it and I discretize it, I have this algorithm that is the whole thing that is written here. It looks a bit, oops, okay. It looks a bit big, but it's just discretizing what is above. And I have two terms. One that is an interaction between each marginals that will bring all my marginal close together and make all the marginal trying to be on all equal, which is what the transport is trying to do, is try to make all the marginal equal or close to each other. And then there is a second part that is an interaction between the same marginal, but all the particles that is going to try to put all particles, spread all the particles so that they resemble, they are close to what they're supposed to sample. And this is supposed to give me a good approximation of my gamma star alpha, which is the minimizer of the f alpha that I'm trying to minimize. I'm just going to show some already numerical experiments. Because regarding the algorithm, it's pretty much all we have for now. So I'm going to start with the drawing on the bottom. So here I just have dimension 1. I just have two marginals. It's the simplest case we can find. And we have 50 particles, or I think more or less. And we start on this drawing, on this graph at the bottom. We start with the green points that are the starting particles, and we make them evolve and with this algorithm. And we see that they go toward this golden line, which is a transport, the optimal transport from the two marginal. And the red points are the ones that we have at the end. And if we look at each marginal, and the barycenter is what we have there. So the first marginal is a gray line here. The second marginal here is the other gray line. Oops, sorry. And when we take the average of these two marginal, or the average of these two particles, we have some distribution, which is the blue one over there. And the black one is the true barycenter that we're supposed to be close to. Here's the same thing, but with 3 marginal. So that's why we have this 3D drawing at the bottom. So we are again in dimension 1. We have also, I think, about 50 particles. And we have the same thing that happens. So it seems to be working. We have our green points over there that are the one where we start. The black line are how they move. And at some point, they arrive pretty close to this golden line, which is the support of the gamma star that we are trying to approximate. Okay, so what we've done so far is trying to understand if F alpha is a good thing to consider and to minimize, namely if we minimize F alpha and get our gamma star alpha, and look at the barycenter associated to this, which is the push forward again with the average in the underlying space of my gamma alpha star. This mu alpha star, which is my approximate barycenter, is close to the true barycenter mu star. This might not be true in general, because in particular, mu star might not be unique. So it doesn't even make sense to ask this question. However, again, Carlier showed that if one of the mu i's is absolutely continuous with respect to Lebesgue measure, then mu star is unique. And we can see that in this problem, it's not very hard to see that in this case, mu star alpha is also unique, so we can talk about the proximity. And the key ingredient, or the key assumption that we make for this, which actually what the important part of the talk is the following one, which we call a variance inequality, which we can write again, rewrite as an excess, like the first part is variance at mu. The second part is the variance at the minimum. And so this inequality is also called quadratic growth inequality in optimization, because we are asking that around the minimum, there is a quadratic growth of my function f. And in particular, if we suppose that this happened for a positive k, this implies that there is a unique barycenter. And at the exact extreme point where k is equal to 0, then we end up with just asking that mu star is a barycenter. So for this happening for a small k is something that we hope could happen easily or very often, as soon as we have a unique mu star. And from this variance inequality that I will go back to in a minute, we were able to show that the mu star alpha, which is the minimizer of my f alpha, or the barycenter associated to the minimizer of my f alpha, is close actually to my mu star with a rate that is 1 over alpha. So we had an extra assumption that the marginals from which we want to take the barycenter satisfy a Poincare inequality. Actually, it's not very necessary. We have a slower rate without this. But the important part being, I think, the variance inequality. And so the variance inequality with constant k, this k arrive here. So when does this variance inequality hold? So to try to understand where does this variance inequality come from, or like when does this happen, I'm going to go back on my drawing on spheres and see, try to get some intuition of what could happen. So I'm going to look at the sphere. And I know there is one typical example where there is no unique barycenter, which is if I take 1 point x1 on the North Pole and 1 point x2 on the South Pole, every point on the equator will be a barycenter. So I know that in this case, I don't have uniqueness, but I will need uniqueness to be able to ensure that I can approximate my barycenter. I need to have it properly defined. So in this case, I'm in the case where I have non-uniqueness. What I can do is once I have these 2 points, I can, so I have my x1 here, x2 here. I can choose a barycenter that is on the equator and call it x star. And then I will draw the geodesics that start from this x star and go to x1 and x2. And I pull my two x1 and x2 closer to my barycenter. So I end up with 2 points here that we call x2 minus and x1 minus, because they become closer, so they have a distance inferior, it become closer to my x star. And in this case, it's I start to have uniqueness. X star becomes my unique minimizer. And I'm hoping that things are more stable in this situation because all points are closer to x star, and I'm closer to the tangent space. Like everything is closer to the tangent space that I didn't really define here, but or mentioned before. But hoping that everything is close to the tangent space and closer to the Euclidean case where everything is working well. And there is a third example that I want to mention is the opposite, where I still have my 2 points x1 and x2, my south and north pole. I choose the same x star as the barycenter, and this time these geodesics that come here, I push my x1 and x2 on the other side of the sphere. So I would have on the other side of the sphere my x1 plus here and x2 plus here. And in this case, since I reach the non-uniqueness when I'm pushing further, x star is not barycenter anymore of my new not barycenter of x1 plus x2 plus. From this drawing, the hope we have is that once we have our two measures, our points around our barycenter, if we're able to push them away from their barycenter and still having the same barycenter, we're hoping to be in a case where everything is behaving well and have a variance inequality. This is not a proof, but this is the intuition behind why the following theorem is true, which is when I have x star to the barycenter of some points on the the barycenter of points x1, xn with the weights on a positively curved geodesic space, just like the sphere and over the space. If I push them away from x star by a factor 1 plus lambda, I end up with my xi plus that I defined here. And if xi plus have the same barycenter x star, then I satisfy a variance inequality with constant lambda over 1 plus lambda. Okay, so now how does this translate for the Wasserstein space? What does it mean to be able to extend the geodesic for the Wasserstein space? So it's pretty easy to check. So my geodesic from 2 points, sorry, so I won't have time to do it, so I'm going to skip it. But it's pretty easy to check that to extend a geodesic is asking that the transport map is the gradient of a function that is not convex, but lambda over 1 plus lambda convex. So I ask strong convexity of my potentials instead of just convexity for the potentials that emanates from my measure mu star toward the mu i's. And there is a result by Sino and Austin and their collaborators, Tyler and Philippe, that shows that. So if the mu star, so it's a corollary to be exact of what they showed. If mu star has a density with respect to Lebesgue, the absolute continuous with respect to Lebesgue, and the support of mu star is whole RD, if all convergence potentials are alpha I strongly convex, then you satisfy a k-variance inequality that is the average of this alpha I. Okay, and so since I'm going over time, the last slide of some few numerical experiment. So the typical case where we don't have uniqueness is I take one, let's say I'm in dimension 2, I take one Gaussian that is supported on a one-dimensional vertical space. I take another Gaussian that is supported on a one-dimensional horizontal space. And what we did here as an experiment is we inflated a bit these Gaussians so that they have RD as a whole space, but they have for covariance matrices epsilon 1, 0, 0, and the same thing where 1 and epsilon are inverted. And we see that so the real barycenter of these two measures is supposed to be the level, the one that the one with the level set that are black here, and instead we have these red dots that our algorithm is giving us. And in this case, we have an alpha that is very small. So in this case, the algorithm is not working very well with a small alpha. But as we increase alpha, we see that we're going closer to what we're supposed to obtain. And in particular, in gray here, this is marginals. The marginals are getting closer to what they're supposed to be, which is Gaussians. So we have a lot of work to do. In particular, so I'm writing what rate of convergence, but convergence itself is not proven either. We don't have the function f alpha is not geodesically convex, so we cannot apply simply this. What would be the dependence on the dimension is another thing that we would like to understand. I didn't mention why we chose SVGD to compared to other potential ways to sample from the marginal, but there is one reason that I can talk about offline. And the other thing is, so this is related to unbalanced problem, because Kyle divergence that we added the to replace the constraint allow us to have measures that are not necessarily with the same mass. And so how does this work in this case? And also another interesting question, I know some people are interested with other costs, but this variance inequality, I don't know what they mean with this other cost. I don't have this interpretation. So this is another open question. And that's it. Thank you for your attention.
Any questions?
Yes. So why SVGD? You said you have a justification.
Yeah. So we want to arrive. So if you remember the drawings that I did, there was the experiment that we had. There was a golden line, which is a transport where we want all our points to arrive. And if we look at, for example, a Langevin, so if I have one particle and then I apply a small Gaussian to it, then I know that all the time I will jump out in a direction outside of this, while I want everything to get fixed in this. And another thing is the direction in which it will jump will depend only on the grad log of mu I. And this information is not enough to know what is the optimal transport. So a single particle doesn't have enough information to know in which direction it needs to go. It needs to have information from all the particles to have an idea of what the optimal transport is, to know in which direction it's supposed to go. So we need something that is deterministic or just traveling along the transport maps. And we need something that knows about all the particles to guess, well, to estimate this transport map implicitly.
Okay. Thanks.
Any other questions? If not, let's thank Thibaut again.